Hi everybody. So today I'm gonna present some results of the work I've done during my PhD in Luxembourg under the supervision of Professor Geoffrey Caruso. And it's entitled Linking Urban Landscapes to Ecosystem Services and Carbon Balance, and with a European perspective here. So the CO2 concentration increased by 48% across the globe since the pre-industrial era, to reach 415 ppm last February 2021. It is above the planetary boundary associated to climate change, which has been set at 350 ppm. Planetary boundaries are finite and they correspond to thresholds of the Earth system for life to remain safe. Carbon dioxide, or CO2, is a key driver in climate change, which is a global issue, yet CO2 concentration is not homogeneous across space and across time, as shown by the publication of NASA that you can see on the right side with the first three plots. Flows are driven by meteorological features and do not end up in an homogeneous global concentration. We can observe geographical variations in the location and of source and sinks of CO2. For instance, 3/3 of emissions from anthropogenic activities are emitted in cities, as they gather an increasing proportion of the global population, yet they represent a tiny proportion of emerged lands. And the map proposed by Zhang et al. That you can see on the bottom right is showing the maximum daily photosynthesis capacity across the globe. And they show that the carbon sink vegetation sequestered about 36% of global emissions in the period 2010 to 2019. These geographical variations are also visible at the urban scale. And this is the focus of the work I am presenting today. So my PhD research focused on the capacity of cities to respond locally to the global climate change challenge with a spatial perspective. Urban forest ecosystem services are seen as a regulation tool, especially for the carbon balance. This work tried to answer the following main question, which is how do urban spatial configurations impact UFES and carbon balance? But before to go any further, here are some key definitions to keep in mind. First of all, the term urban forest does not correspond to forest land within an urban area, but instead includes all elements of the vegetation within an urban area, as it is defined in the field of urban forestry. Second, ecosystem services are all ecosystem functions providing a benefit to human beings and societies. And the term UFES, or here urban forest ecosystem services, correspond to ecosystem services the urban forest provides to urban inhabitants and urban ecosystems. So here are the main research questions I tried to tackle during my PhD to try to assess the role of urban structures. So first, what types of urban structures are present in Europe? How is the urban forest integrated within urban landscapes? Second, how does the urban structure impact the demand and supply of regulatory ecosystem services? Third, how does the urban structure impact the carbon profile and the carbon contribution of urban areas to the global cycle? And last, can a high resolution and standardized method be developed to estimate urban carbon flows based on land use data for replication and for comparison? So this presentation will be split in mainly two parts. The first one will present a bit the methods used and some results I had with the urban forest ecosystem services. And in the second part, I will talk mainly about the urban carbon flows. So here I will start presenting urban structures and integration of the urban forests in European cities and show some results with the UFES scores and ranking of cities. So The ecosystem services provided by the urban forests we focused on during this research are the following. So evapotranspiration and shading to regulate microclimate, sequestration of CO2 to regulate macroclimate, air filtration and deposition of gases and pollutants, soil permeability to regulate rainwater runoff, and improving mental and physical health via the view and access to natural lands. We am at answering the first research question, which is what types of urban structures are present in Europe and how is the urban forest integrated within urban landscapes. To do so, we followed as you can see. So we used the Urban Atlas 2012 high resolution land use database for 689 functional urban areas in Europe. So here I highlight the fact that I mentioned functional urban areas, which means that we looked at urban areas defined based on commuting patterns around the urban core of cities having more than 50,000 inhabitants. And we did not look at the actual administrative boundaries of the cities. And the reason is simply because this functional definition takes into account anthropogenic activities, so commuting from residential areas to workplace, for instance. We computed a large set of metrics to characterize the urban structure. There are 3 types and correspond to first the proportion of different land use categories, the proportion of vegetated land within a buffer around anthropogenic land, such as residential, the proportion of vegetation around residential areas, or proportion of vegetation around the transport network, for instance. And the last category is landscape metrics to describe the spatial configuration and organization of different land use categories. So for instance, to assess the degree of compactness or cohesion of different patches of land use. From the selected metrics, we executed a clustering using the HCA algorithm. So HCA stands for hierarchical clustering analysis, and created scores to be that will be presented right after. So the clustering algorithm allows to characterize the cities into 10 groups, which can be gathered into 10 clusters, sorry, which can be gathered into 4 main groups of cities. So they have been labeled as follows. So in blue on the top left, you can see the box plot for the metrics for standard European cities. So they are called standard European cities in the sense that most of the values they have for the different metrics are rather close to the average for the study area. So for these 689 cities. On the top right in green, you can see the forest cities. Bottom left, you can see herbaceous cities, and bottom right in red, you can see anthropogenic cities. But to have a more visual overview, we can look at this sort of catalog of the clusters and observe some trends. So on top, you have the forest cities, and they are characterized by large forest cover with different levels of connectivity between the forest patches, yet the degree of spatial integration of the urban forest within the urban area varies quite a lot across the different clusters. So this group has 4 clusters. In blue, you have the standard European cities that tend to be polycentric cities, for which the urban core is first surrounded by agricultural land, usually, and natural lands such as forests, wetlands, when there are some herbaceous land, tend to be located rather away from the urban core. In pink, you can see herbaceous cities that has 2 clusters, one which is having as predominant vegetation, herbaceous vegetation, and the other one having as predominant vegetation, herbaceous, and or wetlands. They also have a rather small impervious cover. And last, the largest group actually that contains 3 clusters, anthropogenic cities. They are characterized by a rather compact urban core and low amount of vegetation, but the highest proportion of what I call artificial green. And by artificial green, I mean urban parks, leisure infrastructures, and so on. Yeah, so now if you look at this map, that is actually zoom in. So I have a few more cities up north and up south and in the south for Spanish islands. So we can observe some geographical trends in the location of the different clusters. So for instance, if we look at the standard European cities that are the blue points, these ones are mainly located in central latitudes, but herbaceous cities that you can see in pink and purple are mainly located in Southern Europe, going from Portugal to Turkey. And if we look at the anthropogenic cities, we have 2 main trends. So the clusters A1 and A2 that are visible in red and orange are located mainly along the Manchester-Milan economical axis and expand towards Denmark as well. But the cities from the cluster A3 in yellow are mainly located in Eastern Europe, so in part of Poland, Romania, Bulgaria, but not only. Something else interesting to look at is the area which are highly likely to face, for instance, heat wave or water stresses, heat and water stresses in the future. If we look, for instance, at Northern Europe, and Northern Europe in a very large sense. So if I look at the UK, Belgium, Netherlands, the Nordic and the Baltic countries, it has been proven that they will face an increase of the water discharge in the future. But then if we look at the cluster from which those urban areas are belonging, we can expect that Nordic cities will be maybe less impacted because they belong from the group of forest cities, which are characterized by more vegetation within the urban core, and also less compact anthropogenic lands. While most of the cities in red, so you see Belgium, Netherlands, most of the UK, are characterized by very dense urban core and low amounts of non-artificial green, I would say. Sorry. Yeah. Now a second aspect is the second research question. How does the urban structure impact the demand and supply of regulatory ecosystem services? So in order to assess the balance between the demand and supply of the 5 ecosystem services considered, we computed scores for each of them using budget values following the Burkhardt approach. Values are ranging from -5 to 5, such that a negative value is associated to a demand and a positive value is associated to a supply. So scores are weighted means of the standardized spatial metrics that I present, that have been kept in the analysis. Initially, Burkhardt proposed weights for each combination of land use and ecosystem services that are indicated here with the arrows on the side of the table. And we extended the weights to landscape metrics based on our literature review. So there is still a need to do a sensitivity analysis to assess a bit more uncertainty, but this should be taken more as a guide, let's say. And then the global score is computed as a simple mean of the 5 UFE scores. So now if you look on the right side, we can see the 689 functional urban areas studied, ranked from the highest global score on top left to the lowest global score on bottom right. And some of the most populated cities are also visible in gray, but I'm not sure you really can read. But yeah, so we can observe that there's a rather clear behavior for the groups forest cities and anthropogenic cities that are the green ones and the red, orange to yellow ones. When looking at the box plot on the left for each cluster, we see that the forest cities tend to have the highest scores, while anthropogenic cities tend to have the lowest scores. But when excluding the clusters F4 here and A3 in yellow, these two groups' values are barely overlapping. If you look at the range of values. Yet we observe some variability among the clusters, and the trend is not as clear for the cluster from F4 to A3, all the ones in the middle. What we can say from these two graphs is that from cluster A1, full cluster A1 and A2, the demand for regulatory services from the existing urban forest is more likely to exceed its capacity, while the forest cities and wetland cities are less at risk, I would say. It is interesting, though, to note that cities from clusters F1 and F3 tend to have larger forest covers than cities from the cluster F2, which is the first one here. Yet F2 has a significantly higher global score and individual UFE scores. And this can be explained by a much higher degree of integration of the urban forests, and more particularly its forest land within the urban areas. As concluding words for this first part, here are some elements. So 689 European cities have been characterized in terms of urban structure and spatial integration of the urban forest within urban landscapes. We propose a typology of European cities summarized in 4 groups. And what we can also extract is that compact cities with a low amount of natural land and low levels of integration of the urban forest are more likely to face urban stresses in the future, meaning that the ecosystem services supply from the urban forest is less likely to satisfy the demand from the anthropogenic behavior and pattern. And last, the quantity of urban forest is important, but the ecosystem services supply is greater when increasing the degree of spatial integration of the urban forest. So I'm now jumping to the second part, focusing on the urban carbon balance aspects. I will first present the model and then show rather quickly some results at the European level. So the main research question I will focus on is actually the last one. So can a high resolution and standardized method be developed to estimate urban carbon flows based on land use data for replication and comparison? So here I will be a bit generic in the type of input that I've been using in the model, and I will also mention which data I've been using more specifically, simply because this model could be replicated at different period of time for different locations with different data if the quality of the data could be improved, for instance. So in order to run the model, we need 5 types of data. First of all, a land use database. So here we use the Urban Atlas 2012, sorry, that I presented a bit earlier, which is available for about 800 European cities, European urban areas, and that have the detail for 29 land use categories. Second, we need the CO2 emission spatial database, preferably with emission per sector of activity. And here we use the TNOCAMS database, which distinguishes anthropogenic activities using the SNAP categories. And SNAP stands for Selected Nomenclature for Air Pollution. And you have description of the different categories considered. Some have been aggregated, as you can see, like 3, 4, and the class 7 has been split in 3 subcategories, actually. And also, I do not consider SNAP number 9, which corresponds to emissions associated to waste management, simply because there is too much uncertainty with the data, the database from the TNOCAMS, simply because I think they have most of the time national data, and it was rather hard to have it spatially explicit across Europe. 3, so we also need the characteristics on the vegetation. So part of it should already be provided by the land use database, but it can also be completed with data such as the tree cover density or the tree types, for instance, which we did for the model using data from Copernicus mainly. And then the last 2 input data are actually available globally and not just for Europe. So first, we need to apply temporal decomposition on both emissions and sequestration estimates. So we start from annual emission at a specific location, and the objective here is to be able to downscale it from annual data to monthly and then daily in the sense 1 typical day per month for a specific year. And this for both emissions and sequestration. So we used data from Zhao et al. That I will present a bit after, and the decomposition factors from TRIPA for the emission. And finally, the global ecological zones and their associated climatic domain that are used to calibrate the model. Because as I will explain a bit after, for the model, for the emission part, we use the IPCC guidelines, and they are using the ecological zones and climatic domains, to calibrate and change the value of multiple parameters. So the UCB model contains 4 main steps. The first one, we downscale spatially anthropogenic emissions, which are initially available at a spatial resolution of about 7 per 7 kilometers. So this is from the data made available by TNOCAMS. And we use the land use database to downscale the sectoral emissions to the land use categories from which they are emitted and express the annual emissions in ton of CO2 per hectare for each sector of activity. Then in the second step, we estimate the sequestration capacity of the urban forest in tons of CO2 per hectare following the IPCC guidelines. It depends on the type and characteristics of the vegetation as well as the ecological zones. The third step, we apply the temporal profiles. So first on the left, you see for the emissions, and on the right side for the sequestration. So for the emission, we use monthly and weekly emission factors, which depends on the sector of activity, the country, and the year of interest. The daily maps correspond to an average Monday here of each month in terms of anthropogenic emissions. And then for the sequestration, we use the GPP MODIS product from NASA. So GPP stands for gross primary production, which is location specific and year specific as well, to obtain monthly decomposition factors. And then the daily maps correspond to an average day of each month in terms of sequestration capacity. And the last step, but I will not focus too much on it, is spatial dispersion of the emissions, which I worked on, but in the end I realized it was not, let's say there is way too much homogeneity in this aspect. So the idea was to simulate the spatial dispersion of emitted CO2 molecules following a steady state meteorological condition, meaning no strong wind or main wind direction. To do so, we used the 2D Gaussian isotropic dispersion matrix, and the dispersion parameter sigma can vary. We apply this dispersion to the sequestration filter, basically. But the model can be used without this step, and then it provides a balance for each cities. And then regarding the results, so one very important element that appeared is that for some cities, there are two sectors that can be very dominant in the total emissions, which are SNAP 1, corresponding to energy industries, and SNAP 34, 34, that corresponds to industry, combustion, and processes. And we realized that it was a real limitation in the approach, in the sense that for some cities, they can represent more than 80% of the emissions for quite a large number of cities. And then in the situation where the energy industry are predominant, it can also mean that the level of emission is also very high for the urban area. And in that case, then the power of the sequestration from trees is way more limited, simply because you need way more vegetation than the urban area can host to actually capture what has been emitted. So that's one very important limitation that has been spotted. But now here are some, I think, interesting results to look at. So here are 4 cities that are from the different groups highlighted by the typology. So Sarajevo, Newcastle, Faro, and Tilburg. So Tilburg is an anthropogenic city. Faro is a herbaceous and more precisely wetland city. Newcastle is part of the standard European city, and Sarajevo is more considered as a forest city. So in order to have a wider view on the potential mismatch between the capacity of the urban forests to sequester anthropogenic CO2 emissions and the actual emissions, we can look at the relative daily emissions expressed as a percentage of the sequestration capacity. So the smaller the value, the better it is, and 100% on the left side, so the red plot, 100% is the reference. So we can see that there is a lot of variability along the year, which was expected, and more emission around the winter. But what is, so basically for Sarajevo and Newcastle, values are always underneath 100%, so a maximum around 45% for Sarajevo and around 85% for Newcastle in December, which means that from an aggregated point of view, these cities are not emitting more than they are able to sequester, which doesn't mean that they are able to sequester all what they are emitting, but in terms of carbon balance, they are in a positive situation. Then if we look at Faro, for instance, we see that in November, it goes up to 304%, meaning that emissions on a typical day in November 2012 for Faro were representing 304% of what the vegetation was able to sequester. And then when we look at Tilburg, so anthropogenic but still small size city, so I picked on purpose some urban areas that were rather comparable with some limitations, but still rather comparable. So there is no huge city, there is no tiny, really tiny city, let's say. But we see that for Tilburg, the minimum relative daily emissions represents 490% of the sequestration capacity. That's the minimum, and the maximum goes up to 14,640%. So we see a really big mismatch, and which is here we cannot see directly, but it is not always related to the absolute capacity of the vegetation, as it is the case here. So to conclude on this second part, so first of all, this work represents the first high-resolution CO2 emission sequestration balance model for urban areas, and it has been calibrated. So it is a calibrated spatial temporal model for urban CO2 balance, but it could actually be used for other gases, simply because the method of downscaling could be replicated for other gases, and the decomposition factors provided by CRIPA for the emission factors are available for other greenhouse gases as well. The method considers sectoral emissions and applies spatial downscaling based on land use data and temporal downscaling based on sectors, year, and country. And the UCB model can be replicated for other locations or time periods, as I was saying a bit earlier. It is also, so it allowed to create the first high-resolution urban carbon balance database for 802 European cities, which means the creation of an anthropogenic CO2 emission spatial database per sector of activity at a spatial resolution of 1 hectare and available at annual, monthly, and average day per month temporal resolutions. Aggregated data per sector and per city are also available. Another product is the Urban Forest CO2 Sequestration Capacity database that is also available at the same spatial and temporal resolutions, plus aggregated data per city. And to finish, carbon balance in relative and absolute terms per average day per month is also available. So in this part of the work, we identified some European carbon profiles. Yeah, so cluster, like, even though I did not, for lack of time, did not enter into the details for the carbon profiles and the link with the clusters, we've been able to identify that clusters with a high level of integration of the urban forest have a better relative carbon balance. And that the predominance of some industrial sectors can represent a limitation, as I was showing with mainly industrial sectors and energy sector. Yet we characterize urban structures, which can be beneficial to policymakers and urban planners to act on the urban carbon balance. So now some concluding words on the general contribution of this research. So we explored the geographical variations of a global challenge at the urban scale for an entire continent, exploration of intercity variations, and mapping of intracity variations as well. So in this work, we did the downscaling and analysis of anthropogenic CO2 emissions for more than 800 cities. We estimated sequestration capacity of the urban forests for those cities at a high spatial resolution. We also characterized the different urban structure types that are present in Europe and investigated the link between the urban structure and the European carbon profiles. And to finish, we also investigate the link between urban structure and the demand and supply of regulatory ecosystem services. So that's it for me. Thank you very much for your attention and for the invitation, and I'm awaiting for your questions and for the discussion. Thank you.
Thank you very much, Marlène. This was really a very, very interesting talk, and also very relevant, I would say, because it's a very important topic right now. So thanks for sharing your work. It was very interesting. So I'm sorry I didn't mention that at the beginning of this talk, but you can type your questions on the chat. I will read that, or you can also raise your hand and then speak up. So either way is fine. Yeah, Mark here is appreciating your slide, and also very interesting and timely work. Yeah, definitely.
Thank you very much.
So as a start, I do have a question on all this. I mean, you presented really a lot of things, so
yes,
it's wide. So I would start with something that relates to the first part that you presented, so around the typology that you created, and then you did this ranking in relation to how demand and supply are, let's say, balanced across the various typologies, basically. So my question is very much related. So when you create the typologies, which are very interesting, you also have this cluster of compact city, which probably, I mean, I've been working on the idea of livable cities, and compactness is an element that is very important, right, to make a city more livable and in theory more sustainable, right? But in your ranking, basically compact cities come up down at the bottom of the rank, right? So yeah. I assume that is because you basically have a wide variety of cities in terms of population as well, right? And then correct me if I'm wrong. So my question is basically if you had a look also at how these typologies shape the balance differently across similar kind of population size cities. So if you've looked at this ranking, but comparing, let's say, cities with the kind of similar demand in terms of ecosystem services. So
yeah, so thank you for your question. So I actually investigated this a little when I was exploring, like when I had all my final results, and I wanted to try to see if I could have a different perspective on the result, because that was not the initial focus. But in the end, it was not really significant. And what I saw is that there is a big difference between the cities that are emitting the most and the ones that are emitting the least. And I mean, I didn't really knew what to expect, but I did not investigate this very deeply. I just did rather simple regressions. And I don't have the result really in mind right now, but I remember that it was not significant, the link between, is it the link between the emissions and also like the different clusters, right?
Yeah, and population as well, I was thinking.
Yeah. So log of population and emission,
Yeah.
and seeing if there is a link, if there is a differentiation along the clusters. And I did not really see this. What I saw is that most of the anthropogenic cities were also large cities. So in that sense, I think that I would need to investigate this question a bit more seriously, actually, to find a relevant pattern and have a proper answer to this question. But it came to mind once I had the result, because obviously when you talk about CO2 emissions, for instance, you always think of and the log of the population. But in the end, the first investigation that I did was not really showing something significant. So yeah. And I stopped there by then because it was the end of the PhD. But I really hope to have the time to go back to the results, because I mean, as I showed, quite a lot of material has been created from this work. And I think that it could be investigated much further. So yeah, so I don't have a very clear answer to your question, unfortunately, but
it's absolutely fine. I mean, it's interesting actually that you, I mean, even from your some preliminary results, you didn't find that relationship as strong. But then, I mean, it's nice to have some material for future work, isn't it? So
yes,
that's
exactly.
absolutely good.
And sorry, just to come back to the point you mentioned on the fact that usually we associate compactness to sustainability. I was actually expecting from the beginning that with the ecosystem services I'm focusing on, I will not really find this trend that it's better to have compact cities, because I look also at microclimate regulation, for instance. And then if you have a very compact city, I mean, for sure it will not have a positive outcome. And similarly, if you have a compact city and you don't have, and basically most of the green spaces are on the outskirts, then when you look at mental and physical health, that is also assessed via the proximity or accessibility to green spaces from residential areas or from the urban core. This will also not be very, I was not expecting a positive relationship there. So I think that because of the approach I took and also the ecosystem services I took, it was rather expected not to find out that more compactness is better, I mean, more sustainable, but in this specific case, it's more not helping to the balance between the demand for and the supply of ecosystem services from the urban forest, because there is this need of proximity, and yeah, that was actually one key element, like trying to not look at the city as aggregated, I mean, as a point, but really looking at the city, like at the spatial variation across space in the city, and trying to understand, okay, is it better to have, I don't know, like for the same amount of vegetation, is it better to have a green heart or a green belt on the outskirts or sparse vegetation? I mean, that's what this first part of the work really looked at, like, and that's what this global index shows. In the end, this cluster that I call F2, which is not really, yeah, I could have picked a label a bit nicer for it, but it shows that even though for this cluster the cities are having not the largest cover of natural land compared to the rest of the group, because the green spaces are better integrated within the urban core, then they perform better. And once again, to take with some limitations, because as I mentioned, I still need to do a sensitivity analysis, I think, for this course. I mean, how I basically created the weights for the different metrics. Part of it is taken directly from Burkhardt, but the rest is from my understanding of the literature and should be but I made some variations, just I did not do yet a proper sensitivity analysis, but the trends were always the same. So yeah.
Thanks. Absolutely interesting. So just because you were talking about the score, actually, I have a question very specific to that, because I couldn't look at all the variables that you used to define this score, actually, but I mean, I saw that you used quite a lot, and at least it was like 3 or 4 domains that you've looked at. So and across all Europe. So this is a very kind of sort of curiosity more than anything. What kind of data sources did you use for that, for covering all the continent? Did you pick?
So I started from, so that was the first difficulty I had. So I wanted to use data that is really comparable for all those European cities. So I used the Urban Atlas, which is a land use database available for most European cities of more than 50,000 inhabitants. So now there is the version for 2018 as well that is available, but when I started it was not yet available. And yeah, so the issue is that I'm limited to land use categories. So for instance, when I have the information that here is a forest polygon, for instance, I just know it's forest and nothing more. I don't know, I know nothing about the tree density, the type of trees and that kind of things. So that's why in the second part of the presentation, when I look at the carbon balance, I actually added some extra information on the vegetation with tree cover density, if it's mainly broad leaves or coniferous, and that kind of elements to improve the knowledge on the, yeah. Because so the idea of this work was to have a rather systematic approach for most European cities, to be able to say, okay, this is the mosaic of cities we have in Europe, but obviously it's not as detailed as if I was having access to a tree inventory for all of them with characteristics and also information on wetlands, grasslands as well. It can vary a lot, and also the type of maintenance. But yeah, so the idea was to be able to really compare a large number of European cities. So the need was to have a database that used exactly the same methodology to make the data for all of them. So the Copernicus product was the right alternative at that moment. Yes.
Great. Yeah, I could see the challenge of trying and integrating data across different countries. I mean, in the UK, we have that just within the UK across England, Scotland is always quite problematic. But yeah, I mean, it's good to have European data providers. So yeah, just because if there are no questions for the audience, I have actually a very last quick one that links with the last part of your work. When you look at the carbon balance, I saw actually in your final remarks that you already mentioned that you're looking into the more in depth into the relationship between these typologies and the carbon balance. So yeah, basically my question is very open to what's up now. So basically, what are your future plan to follow up on all this very interesting research that you've done so far?
Well, so as you mentioned at the very beginning, right now I'm doing a postdoc that is more focusing on urban biodiversity. But what I would like to do afterwards is really something that is combining both aspects, because they are very linked. So so now when I talk about urban biodiversity, is mainly wildlife in the city. But obviously, when we look at vegetation, vegetation is habitat for multiple species, non-human species. And yeah, so if I talk only about this carbon balance aspect and the typology, I think there's a lot to do. And I would like, for instance, to, so now I'm working on updating a little some aspects of the database before to publish it properly. But I also would like to have a more recent version of it for 2018, which should be possible. But also trying to look at the urban forest not only as regulation tool, but also like trying to include it to see the city as a whole ecosystem that is, and urban forest that is not only supporting humans and cities and global challenges, but also the biodiversity that is already present in cities and that are quite often actually supporting trees, for instance, or sometimes threatening them. But all of this is interlinked, and all of this is part of somehow the same global challenge. So having a broader, trying to figure out how to integrate both aspects in planning would be something that I'm really looking forward. And that's why right now I'm really happy to gain more experience into urban biodiversity with the planning aspect that is quite important in this project. And if afterwards I can really combine these two works, then I'll be I think there is a lot to do in both fields, and the combination is needed. And yeah, there's really a lot to do, so it has to be done at some point. And it's urgent, I believe. So
yeah, no, absolutely timely. And yeah, so lots of things. At some point you will be able to square everything, actually, I'm sure. So it's
hopefully
interesting. Yeah. For now, sharp. So I think it's time to close this. I want to thank again Marlène. It was a very, very interesting presentation, and I mean, yeah, people are congratulating about your talk in the chat as well. So that was great. Thanks, and we will keep in touch, I guess.
Yes, thank you very much for the invitation, first of all, and for your attention as well. Thank you.
And thank everybody to stay here, join us for this session. Cool. Goodbye, everyone.
Thank you. And if you have any further questions, do not hesitate to contact me as well. Yeah, I'll be more than happy.
Cool. I will circulate your email in the chat for the lab.
Okay.
Cool.
Thank you.